Okay, so as promised, I wanted to just give an example of how to do a proof for the eGas project. And what I'm actually going to do is just to go ahead and prove the parallel and perpendicular lines theorem. So that'll be one less proof that you need to do for eGasp. I also want to remind you, you do not need to prove the alternate interior angles theorem. We need a starting place. We need something that we can that doesn't need to be proved because we have to. And note, there's a little note here that says that the alternate interior angles theorem is, this little thing here means that it's basically logically equivalent to the parallel postulate. So if we grant the parallel postulate, we get the alternate interior angle theorem. And so we're just going to go with that. That will allow us to, it'll give us basically what we need to prove the parallel and perpendicular lines theorem, as we'll see. So let's just take a look at this statement here. And because one of the first things that I need to point out is if you have an if and only if, then it's really actually two proofs, one for each direction. Let me explain what I mean by that. So this says two lines are parallel if and only if they are both perpendicular to another line. And then we get a little bit more here. So we're talking about we have these three lines, and if L is parallel to M and N is perpendicular to M, then L is perpendicular to N also. Right? So basically if N is perpendicular to one of those parallel lines, it's also perpendicular to the other of the parallel lines. That basically, so that's kind of one direction. The other direction is that if a line is perpendicular to two other lines, then those two other lines are parallel. So let me just, I'm going to move this aside for the moment and we'll kind of zoom this out a little bit. I'm going to kind of show how to do this. So these are kind of the two statements that are given in this theorem. So again, so one direction of this proof is to say that if L is parallel to M and N is perpendicular to M, then that's what it means. It implies that L is perpendicular to N. The other direction says that if N is perpendicular to M and N is perpendicular to L, that implies that L and M are parallel. So to prove this, we need to break it into two parts, and we need to do each of them separately. So I'm going to do this direction first. All right, and you might include this in yours, in your proof. Kind of tell me which direction you're proving, right? Because what you start with and what you're trying to prove is going to be different in each case. So I would start with, that lines L and M are parallel. And line N is perpendicular to line M. And this is, you could say this is given. And then, I think it's helpful to just say what you're going to show. We will show that L is perpendicular to N. So here's our givens. This is what we want to show. So let's start with what we have. I think it's also helpful. I want to just point this out. It's helpful to have a diagram to refer to, but a diagram is not a proof. All right. So let's go ahead and draw a diagram, and I'll explain more about what I mean by that. All right. So let's call this L and this M. We're going to put in a third one, and we'll call that N. Right? So in terms of givens, we know these are parallel. And then we know that, if N is, here we go, N is perpendicular to M, right? Then we have a right angle here. Now, what I want to do, so let me just kind of back up here. The big idea, I'm going to use the alternate interior angles, right? So if I can show that this is also a right angle right here, because we know from the alternate interior angles theorem, so bring that back here, that if two lines are parallel, then the alternate interior angles are congruent. All right. So the alternate interior angles, if I call this one an angle, then over here this would be the alternate interior angle, and I want to show that that is also a right angle. Therefore, N is perpendicular to L. All right. So to refer to these, I need to fill in some points so I can refer to these angles more easily. So let's just call that A. We'll call this one B. Maybe we'll put C over here, and then put D over here. That will allow us to refer to this angle as DBA, and as this angle up here is BAC. All right. So where do we begin? Well, we know that. So we have that L is parallel to M. That implies that alternate interior angles are congruent by the alternate interior angles theorem. All right, interior angles theorem. Okay. And then we might say, in particular, because this means all alternate interior angles, we're concerned with these two in particular. So in particular, angle DBA is congruent to angle BAC. All right, so we know they're congruent. All right, that's a start. Now what? Well, we have to kind of unpack this whole thing about what it means to be perpendicular. So this is where I want to show you how you're going to need to use. What does it mean? So this, let's see, we have perpendicular. Two lines are perpendicular, because that's what we're given right now, right? We know that they're perpendicular. We don't know anything else. And this is probably the hardest part of the proofs, is trying to forget what you know, right? Because immediately you want to call that a right angle. You want to say it's 90 degrees. We need to unpack all that stuff based on previous results, right? So we're working on C. We can see, what are we working on? CT025. We can use everything above it. We've already used the interior angles theorem. Now I want to unpack this whole thing about perpendicular, because that's going to tell me something about the measure of DBA. I've written it in there as a right angle, but we ultimately still need to unpack this whole idea of perpendicular. So just drawing this is not a proof. Right? I'm kind of reminding myself, yes, we know that that's perpendicular, but I need to cite things that come previously, right? So let's see, move this over where you can see it. So we have two lines are perpendicular if and only if they meet to form right angles, all right? So, and what is that? That is BT025. So I'm going to say by BT025 with N perpendicular to M, then we know that angle DBA is a right angle. Okay, now if we go back here, we want to say, because ultimately what we'd really like to say is that BAC is also a right angle. So you might be tempted to say, well, any two right angles are congruent. Well, that's true, but we don't know that we have two right angles. All we know is that they're congruent, and not all congruent angles are right angles, right? So we're going to have to get at that in another way, right? We know that they're congruent, and we know that one of them is a right angle. How are we going to unpack that? So one thing we know is that a right angle has a measure of 90 degrees, right? So we know that, so that's B, what, T020. So by B T020, the measure of angle DBA equals 90 degrees, right? Because DBA is a right angle, and then by BT020, that means that it has a measure of 90 degrees. What we'd really like to say is that that means that the measure of angle BAC is also 90 degrees. All right, so let's come back here again. Let's see. So here we see that if two angles are congruent, then their angle measures are equal. Right? So we know that the two angles are congruent, and we know the measure of one of them, so then that would give us the measure of the other one. So let's say by, what was that? By BP015. P0, 1, 5. We know that the measure of angle DBA equals the measure of angle BAC. That's just a further elaboration of the fact that they're congruent. And then, and here's where what I really want to do is I want to put these two together. So one way to do that is just to kind of number them. I'll call that result number 1 and this result number 2. So then I can just say by 1 and 2, since this one equals 90 and these are equal to each other, then by 1 and 2, the measure of angle BAC equals 90 degrees. And then here, again, by B T0 to 20, we know then that this implies, and I can only use the implies if it just follows immediately from what precedes it. This implies that angle BAC is a right angle. Whoops, getting off the camera here. All right, is a right angle. Okay, so you can see we're getting in probably to a lot more detail than you thought was necessary, but this is what it means to prove something. We only want to use previous results. We're going to always be citing those to make any claim, any of these claims. We want to be able to back it up with something we've already established. We're almost there now. So just move this up to where we can still see it, and then we'll kind of build on this because I'm running out of space on the bottom of this paper. So we know here that we want to go back to perpendicular lines, right? Ultimately, we would like, if we come back to we would like to show that L and N, right? We want to show that L is perpendicular to N. We kind of have it here. We just need to be able to cite something that says if this angle here is a right angle, then those are perpendicular. So let's go back and see what we have available to us. Two lines are perpendicular if and only if they meet to form right angles. Well, we have the right angles part, right? They form, L and N form a right angle because we now know that BAC is a right angle. Therefore, so we can go the other direction. Again, this is the if and only if. It means that they meet to right angles, then the lines are perpendicular. So again, this is what the if and only if means. It means that they're perpendicular, they meet at right angles. And if they meet at right angles, then they're perpendicular. They're equivalent conditions is a way to say it. So I'm going to say then, building on this, that by, I think that was B T020, is that right? No, T025. By T025 with angle BAC a right angle, then L is perpendicular to N. All right, and that's what we said we were going to show. So now we're done. Like I said, it's probably a little bit more involved than what you thought, but this is precisely why I'm going through this, so that you can kind of see everything that you need to unpack. That every claim that you make has to be justified by something before it. All right. I just want to, fortunately, this proof, going the other direction, is a little bit shorter, but so let's just go through that. Now again, I'm going to say this, we're going this direction, and I'm going to say that N is perpendicular to M, and N is perpendicular to L, and that that's given, and that we want to show that L is parallel to M. All right, this is just, I think it both helps with writing the proof well, as well as making it easy for the reader to know, okay, here's what we're starting with, this is where we want to end up. Okay, again, big picture, if I use the same diagram here, although now what we know is, this is what we know. We know that this is a right angle and that's a right angle. Or at least we can quickly get to that from from this, right? That those are right angles based on B T025. And then, since right angles, well, because they're both right angles, then they're congruent and they're alternate interior angles. So then we come back to, again, this is the if and only if on the alternate interior angles theorem. If they're parallel, their alternate interior angles are congruent. But also, going the other direction, if the alternate interior angles are congruent, then they're parallel, and that's what we want to show. So that's how we're going to get, that's, again, big picture, that's the logic here. We're going to start with these two being right angles, and then get to the fact that they're parallel through the alternate interior angle theorem. So let's see if I can't keep. I want to keep my. All right, why don't we do this? I'm going to fold this over so we can refer to the same figure without rewriting it, and then still start with what we had here. Okay, so let's n perpendicular to m and n perpendicular to L implies that angle DBA and angle BAC are right angles. All right, now I've just made a claim, but I haven't backed it up yet, so I want to back it up by B, oops, getting off the edge here, BT025. All right, you can't see it, but you heard it, and it's in your notes. Let's see if I can move this over and get everything on here. Yeah, pretty close. Okay, so we know that they're both right angles. Okay, now we want to claim that they're congruent. Now, again, this is where, like, you know, in your head, you know they're congruent, but we need to be able to justify that. So again, we come back here, and conveniently, we have BT015 that says that any two right angles are congruent. So, by BT015, angle DBA is congruent to angle BAC. All right. So we don't really need the fact that their measure is 90 degrees this time, because all I need is congruency. Congruency is what the alternate interior angles need, right? I should then state that by definition of alternate interior angles, which you should have previously, we'll have defined that right up here somewhere. Anyways, by definition of alternate interior angles, wherever we've defined that, I'm not going to worry about that too much right now. Angle DBA and angle BAC are alternate interior angles. All right, just shorthanding it right now for the sake of the video to not make it too terribly long. All right, we're almost there now, right? We know that DBA and BAC are alternate interior angles. We know they're congruent. So again, maybe I'll just label these 1 and 2, those results, so that by 1 and 2 and the alternate interior angles theorem, then L is parallel to M, which is what we wanted to show. Okay, you can see why I wanted to show you, though, an example of what goes into a proof. I think a couple of things I want to highlight here just at the end. Again, if you have an if and only if, it's really going to be two proofs. You need to break it into two parts. You need to show one direction, clearly state which direction you're going, and it also helps to include the givens and what it is you want to show, because that further clarifies which direction you're going. All right, diagrams are helpful to give us something to refer to, but drawing a little right angle in here does not prove that it's a right angle. You know, we have to use our previous results to unpack the meaning of what's been given to us. For example, perpendicular lines. What does that mean? It means they meet at right angles. What are right angles? Right angles have a measure of 90 degrees, and so on. So so what I would say is, when you think you have a proof, or if you're looking at a proof that another person in your group generated, make sure that every claim is justified somehow. All right. One thing I'll point out here at the end is sometimes it's just a matter of a definition. You know, if that's what alternate interior angles are, then you can just cite the definition. But again, that definition should have been somewhere in EGAS prior to this point. That's probably the biggest thing, is that whatever you claim, back it up with something that is a previous result, and that's where you'll get very familiar with this, going back and forth, looking for ways to back up your claim. Okay, well, that's all I'm going to. That's about 20 minutes on one proof, but I wanted to be as comprehensive as possible so you have something to emulate as you work on the other proofs. So, real quick, then that leaves you with the same side interior angles, and I think we added the corresponding angles theorem. So it's basically these next two that you'll have to prove.